Some exercise. I picked somewhere, okay, about the exercise. Now, from my point of view, the exercises today, in principle, concludes because we made an exercises on auto coordination evaluation for auto-regressing moving average arma. We made some exercises on basics. We now make exercise on Kramer, and so for me, this concludes the exercises for the intermediate test, which is for next week. Since we have tomorrow, okay, so tomorrow I will pick other exercises randomly chosen, okay, because the topic of the exam next week will be on these macro area, which is stopping on the theory today. Now, so let's get practice over it. Evaluate. So if you got a problem now, beyond the wording of the exercise, okay. So the concept is evaluate the maximal likelihood estimator and the Kramer bound for the model, and the model is xn is equal to a plus bn plus cn squared plus noise. So this noise is describing the noise superimposed in our data, and this noise superimposed is Gaussian with a certain variance. All the noise samples are uncorrelated. Okay. Now let's start with this. So how do you write a problem like this? And suppose that you have a certain number of observations. Okay. So n is 1, 2. I think we use the same problem. For n samples. So I have n samples. Goal is, evaluate the bound of the lower number of samples to get, the variance of b at larger or equal than sigma square b. That is the minimum. Okay. That means I give you a certain minimum value. I give you the noise. Okay. I want to know how many samples should I use, which is similar to who was posing the question. You were posing it. Okay. How many samples? Okay. Now, so let's start. So what I do, I take all my data. I take all my samples. Okay. So I collect my samples to a vector. The vector is n. And then what I need to do is to stack all the unknown on the one side, and I stack all the time samples as a model matrix. So I stack here, and so I have a T0, which is all the time samples that are 0, T1, T2, times A, B, and C. So T is, this T0 is collecting a vector with 1, 1, 1, 1. This T1 is collecting a vector with 1, 2, 3, n. And this T square is collecting 1 to the square, 2 to the square, 3 to the square, n to the square. Okay. So this is what is the content of these 3 column vector plus that. The other is collecting noise. So that means that In our canonic way, this is the matrix H. This is the vector theta, and so forth. Okay. So, what I know in addition to that is that W is, since the samples are white, okay, then I can write that it's normal with 0 me and sigma squared W multiplied by identity. The fact that is identity is because the samples are uncorrelated. Or if you like, is white. These are samples are white. So I wrote the model. Okay. So once I wrote the model, I go to the canonic way. So that means that I can, this is represented as a linear model, H theta plus my W. So I can write, for instance, this case, the Lagrange function, and then I know, because it's Gaussian, the maximum Lagrange estimate. Now, the maximum Lagrange for the linear model in Gaussian is the following: is theta hat maximum Lagrange is equal to H transpose CW minus 1 H, everything to the minus 1 multiplied by H transpose CW minus 1 X. Okay. With you know, usually you have on the back of the exercise. Okay. You, by the way, you need to choose the formulas. Huh? Okay. Remember, you need to choose the formula. So now this is my least square estimate. Now, I mean, for instance, I want to investigate a little bit what is my least square. So since this one is sigma square W identity to the minus 1, and this is equal to 1 over sigma square W times identity. Now, so that means that computing H transpose identity H to sigma square W, everything to the minus 1 is equal to sigma square W, and then it is H transpose H to the minus 1. Okay, so by manipulating, you know. So this sigma square is cancelling with the other, because it's you know, noise is correlated. So that means that theta maximum Lagrange. Now what I'm doing is, you know, if you during the exam you write to me this, it's correct, but you know, you are simply copying the formula. You are not shaping it. You are not trying to understand how this formula is adapted to the problem. This is what I'm doing now. So now, in this specific case, then it is H, suppose H, as I previously calculated, minus 1, H transpose X. Now, for instance, you know, I might stop here, even if I don't like to stop here, but you know, I might stop here. Let me look at the one detail. Since the model is Gaussian, is linear, and Gaussian. solution. Then the Kramer-Rao bound coincide with the variance, the covariance. Okay, that's good news. So when I say I want to find the variance as such that is bigger than that, I know the inequality becomes an equality. Now, what is the Kramer-Rao bound? So in this case, the Kramer-Rao bound is h transpose h to the minus 1 multiplied by CW, which is here, so sigma squared. So that means that this part is something that I need to calculate anyway. So let's make it. So that one is T0 transpose, T1 transpose, T2 transpose. Now these are vector composed, row vector composed of n elements. Multiplied by T0, T1, T2 time everything to the inverse times sigma squared. So let's calculate it in a block partition way. So I have T0 transpose T0. Then I have T0 transpose T1, T0 transpose T2. Now I move to the next page to calculate that. And then copy it. Copy and move to another page. Now, so I have T0 transpose T0. Then I have T0 transpose T1. And I have T0 transpose T2. Everything to the minus 1. Then I have second T1 transpose T0. T1 transpose T1, T1 transpose T2. So T1 transpose T0. That, by the way, is equal to T0 transpose T1. Okay? And then I have T1 transpose T1. Then I have T1 transpose T2. And finally, I have T2 transpose T0. T2 transpose T1. T2 transpose T2. Inverse. Okay. Now let's compute on the side. First of all, this is equal to that. Because if I make row times column is the same as make a column times row. This is equal to that. This is equal to that. Okay? So the matrix is symmetric. As it should be. First verification. Then, let's calculate. So what is a T0 transpose T0? Now, T0 is a vector of 1. So that one is 1, 1, 1, multiplied by 1, 1, 1. Which is equal to n. Okay. Then, I have T0 transpose T1. T0 transpose T1 is 1, 1, 1, multiply by 1, 2, n. So that is equal to sum of n. Okay. Now, okay, so I have done this. I've done this. I will do that. T0 transpose T2. It is 1, 1 multiplied by 1 square, 2 square, n square. And that is equal to sum of n square. Okay? So let me complete that. So this is equal to n is a sum of n is a sum of n square. This is the sum of n. Now, T1 transpose T1 is 1 square plus 2 square plus 3 square. So it is the sum of n square. What is T1 transpose T2? So it is n multiplied, the sum of n multiplied by n squared. So it's n cubic. Now, so here is n squared because it's, here is n cubic because it's symmetric. And T2 transpose T2 is, it's 1 square times 1 square plus 2 square times 2 square, okay, which is the sum of n to the power 4. Everything minus 1. Now, can I simplify? Question. I'm not writing the text of the exercise. I'm simply moving into the exercise because I can make the text such that I'm forcing you to solve different errors. For instance, I can ask you to write the complete form of the Cramer-Rao and then spot into the Cramer-Rao if there are some symmetries that you can exploit to decouple the parameters. Okay, so go. How to decouple the parameters? Now, answer. The answer is, let me say, somewhat simple because the shape here is similar as I've seen before because here I'm summing, so it's 1 plus 2 plus 3 plus 4, but this function is odd, and so since it's odd, if I'm summing into a positive and negative interval, all the sum of odd terms are 0. So, recollecting this matrix to answer the question. How to decouple is by making the sum for decoupling, means making the sum such that they go from minus n odd to n odd. If they are even for n even, or for n odd, they are going between minus n minus 1 divided by 2, 0, and n minus 1 divided by 2. You see, odd and odd means 5, 7, 9, okay? So if it is 9, so I'm summing between -4 and +4, and so forth, okay? So if it is in this case, so if I simply rearrange the parameter in this way, because my goal is to get the estimate of, what was that? One of the parameter. Then you know I'm not interested in how I order the samples. So I simply relabel. And then what I get is the following. Then you know I only have the sum of the terms that are not odd, which means I have n. Now this is 0 because it's sum of n. Okay, sum of n when n is going between n minus nr, and nr is equal to 0. Now I have a sum of n squared. Now sum of n squared now is between minus n half and then half. Then 0. Then I have a sum of n squared. Then n cubic. Sum of n cubic. N going from minus n half and then half is equal to 0. For the same reason. Okay? If I calculate the integral of the function is 0. The sum of all the sequence is 0. So that is 0. Then I have the sum of n squared for the same extreme, 0, and the sum of n4. So now I remember this is -1. So now I remember what was the parameter. Now this one is the parameter A. That one is for the parameter B. This one is for the parameter C. C is, so A is a constant, B is the one that is multiplied by n, and C is the one that's, how can I say, multiplied by n, 1 multiplied by n squared. So what I noticed that from the structure, this is 0, 0, 0, 0. So the matrix, you know, is a partition, organized. So I noticed that the center, the term in the center, is the one that corresponds to B. So I can say that B is decoupled from A and C. Now, if you don't know the sum of the series, and you know, very, let me say, quick and dirty method is to make these approximation. Because I need to calculate sum of n squared. Who is telling me what is the sum of n squared? Okay, I know it's a sum of a series that can be easily defined in closed form, but you know, I don't have the table with me. So I cannot search on Google, I cannot search for the sum of the series. So, and since I need to calculate quick and dirty, so I use very stupid approximation, which makes sense for a larger number. So how to compute? The sum of n squared from minus n half to n half, and the sum of n4 from n half and minus n half without tables. Okay. So I can assimilate this as an integral. Hmm? So that one is approximately an integral between minus n of n of x squared dx. And I approximate the other is minus n of x fourth dx. Okay. So that one is equal to x cubic divided by 3 between minus n of and the other is x fifth divided by 5 between minus n of. Let's continue. So it is n cubic divided by 2 minus n cubic, right? It's not square. Minus n minus n cubic. Okay. Everything divided by 3.
It's again cubic.
Hmm?
Again cubic.
I don't want to use the cubic. See, that's always against my religion, cubic. I like this one. Okay, so and that is equal to, so it is n cubic minus is plus, and so it's 2 times divided by 3 n cubic divided by 2 to the power of 3, okay, which is n cubic divided by 12, okay. Now the second one. The second one is the same story, so it is, and I keep it short, okay? So that one is 2 times n divided by 5 to the 5th power. I try to make it quick, but n divided by 2 to the 5th power divided by 5. Okay. Which is equal to n 5 power
80.
80, right? I trust you, but I trust myself more. Okay. That's it. So now I plug this one into my solution. Okay. Now these are true approximation, true for n much larger than 1. Okay, so I plug in, then I get n. So that. N. 0 n square, which is n cubic divided by 12. Then I have n square, which is n cubic divided by 12. By the way, look at here. These are the same. So I copy simply n cubic divided by 12, n cubic divided by 12 is 0, is 0, 0, and then that is n 50 divided by 80. Everything to the minus 1. I like, if I now I move forward, okay, If I really need to invert this matrix by hand, because I know I need to do it, so what I can do is I rearrange the order of unknown. Okay, which means I'm rearranging the order, which means I am putting B here. B here, A and C, which means it's n cubic divided by 12, then it's 0, 0, 0, 0, then I have n, I have n cubic divided by 12, n cubic divided by 12, and 50 divided by 80. Now the reason is because if I can rearrange, so what I did, you know, I took this entry that is decoupled from all the others and I move it into a corner. I can move there, I can move the other way, so that I isolate this block partition structure. Now, from this block partition structure, when I need to calculate the inverse, I simply need, it's enough that I calculate the inverse of this block. So, if I need to calculate the covariance of A and C, this is equal to the covariance of sigma squared W, which I forgot, of the inverse of n cubic divided by 12, n cubic divided by 12, and then 50 divided by 80. This is because, using the property, that if I have a matrix, I have A 0, 0, A, to compute the inverse for that, this is equivalent to make the inverse of the single block. A to the minus 1, 0, 0, and B to the minus 1. Okay? So I try to reduce my problem to make the inverse for that. So just, you know, just getting a little bit of practice. So if I need to calculate this inverse, then, you know, I need to put a little bit of patience, and then I can find the covariance for that, which is simply blah blah. So I calculate the inverse, and so the goal was to get the covariance on B. So since my goal was to get the covariance of B, then I don't need to make all these trick, which is good. So the covariance, which is now the covariance of B is the variance, so the variance of B is equal to sigma squared W multiplied by 2L divided by n cubic. This is the answer. Okay? Because of the coupling, you know, I'm using this. This concludes the exercise once that I put that, you know, I want that these variance, so if I say variance of the n should be smaller or equal than a certain sigma squared V, which is imposed, and then I get that n should be larger or equal than a certain number.
When we inverse the matrix like that, we basically change the
order.
Actually, yeah, the order first, and the.
Yes, I simply swapped the order between A and B. And the reason was because I want to group, so I want to group the parameter that isolate the block partitioning of the matrix.
I mean, when you are calculating the inverse of a matrix in here,
This one?
no, in here, yeah, I think we
A
have
is
to
the matrix.
change the
B is
A
a
and
matrix.
B.
No change.
No.
They are diagonal. Diagonal means this matrix placed in this way means that, you know, you are putting together two problems. Means that there is a, I don't know, there is a one problem and another problem. And you put together these two problems, but they remain individually separated. Because this matrix does not contain any linking term. If you go to the book, there is one example where I am illustrating this concept in a very easy way. And you know, and when a big math, I mean, when I have a problem, the problem is describing, is linear. It's describing in a formal way by a matrix. And this matrix is, when it's describing, you know, this matrix, if the two problems are separate, but they are just put together, okay? That, as in this case. In this case, it's telling that B, you know, B is just giving the slope, and A is giving the shift, and C is giving the, you know, the curvature. So A is giving the shift, C is giving the curvature. They are both quadratically, so they are both, you know, quadratic dependent. So the linear term and the quadratic term are decoupled in this case, and that's why. Ask me later. So we saw that, okay? Done.
If you go back, why do you say that the interval is between minus n divided by 2 and
Because I have n samples.
and you can also say the interval between 0 and n, right?
Oh yeah, you can say that. But you know, I mean, since in my, where is it? Okay, since my goal is to get B, okay, so I can do everything I can, because my goal is to get B. Huh? So I can do everything I can in order to decouple B from the others. Since my goal is to get B. The other, if you like, A and C, you know, might be nuisance for my problem. And so I simply rearrange that. Simply count it. Because this is just a label. So it's a way to labeling the sample. Okay?
How do you know what
I mean, in this case, it's very, when you look at that, when you're here, you look at that, you have this, you know, this sum. You need to coolly, very coolly understand that the sum of, you know, is like the integral of x. If I make the integral of x from 0 to a certain number, then it's different from 0. But you know, if I make the integral of x between minus and plus the same value, is 0. Now I have another example of similar, which is taken from another example. I think there is nothing else to say on this exercise. I have another one, which was very nice. Now, you know, I simply copy paste from the past, but you know, let me tell you on specifically. Then I go to your question. Okay. Now, imagine that I simply copy pasted, but you know, I want to rephrase it. So imagine that, you know, and it's okay. So I mean, this was a very nice exercise. So forget about what is on the bottom here. Don't look at the bottom. I don't know how to make it. Okay. And so, you know, imagine that we have a data that are generated from a linear model. But, you know, since I don't know the model order, I don't know if it is linear or quadratic. So what I do, I estimate the quadratic one. And, you know, what I expect? I expect that the quadratic term is 0. So what I'm here, this exercise is to prove you that because you are estimating a quadratic term with 3 terms instead of 2, you are making an error. So when you are over parameterizing the model, you are making an error. Now let's rephrase it slowly. Okay. Now assume, so let the model, the data generated as xn equal to a plus bn plus w. This is the data. Okay, the data have been generated in this way. Okay, so which means that in a matrix form, when I have my vector x, okay, this vector x is equal to t0, t1, all the time samples, multiplied by a n plus w. Okay? So let me call this model as the model contain 1, h1. And these are the parameter data. These data contain the linear term, which I indicate as 1. Now, I don't know the data. I don't know the order. So what I do as n? For me, so I guess that the real data, so the x, are obtained by a quadratic model. Okay. Remember, this is the true one. Huh? Are obtained by a quadratic model. What does it mean? It means that for me, xn is equal to a of the quadratic, which is different from a, the true a. So I indicate, so this is a label to recall that parameters are for quadratic model. So I have a2 plus b2 n plus c2n squared plus, you know, I have w prime n. Because w is not the same. So the only is the same is x, the data. Okay? So, you know, what I do here is I write exactly the previous way. So I'm taking the way I described before. So the way I described before is I take x data is equal to, so it is t0, t1, t2 multiplied by a2, b2, c2 plus w prime. Okay. Now, you know, I can calculate. The noise is Gaussian and is independent. Okay? So then what is my estimated value? So what is a2 hat, b2 hat, c2 hat? Now it's I simply borrowed the solution before. So C page, I don't label the page, so let me label the page so we can easily get it. Okay, so we count the pages. 1, 2, 3, 4, 5, 6, 7. Okay, so go to page, here, page 2. See, page 2. Okay, and that is equal to H transpose H. But this H is different from the previous one, so I call this one as H2 because it's including the quadratic term. So this one is H2 transpose minus 1 inverse H2 times X. Now my goal is to calculate the error. So I know what is X. So my goal is to calculate the impact of the usage of more than necessary parameters onto a model that is linear. So what since my goal, let me write it, is to evaluate the interaction for more parameters, I use X for true. So I assume that X is the true one. Okay. So essentially, what I do is I take this one and then plug into there. Because I want to see what is the interaction between the two parameters.
Do we have transpose at the third H2? Yeah. So then-
H2, right? Thanks. Okay. Now, so when I make it, so remember, you have the estimate, okay? So, I have the page. Okay. I copied again. So I have a theta 2, let me write theta 2 hat equal to H2 transpose H2. Then I have a minus 1, then I have a H2. Then instead, in place of X, I have H1. Then I have theta 1 plus no. Okay? So this one is X. So when I plug in, what I get is H2 transpose H2 minus 1 H2
Transpose
H1. You're right. H1 time theta 1 plus H2 transpose H2 minus 1 H2 transpose double. Now, remember, this is A1, B1. And these are the true parameters. On the other hand, I have A2, B2, C2. When, I'm modeling, I'm representing my system with two parameters. So, basically, my experiment is given by a line, and I'm trying to fit with a parabolic pattern. What I expect that the parameter c is 0. Am I right? Because I have data that are linear, and they are generated as linear, and then I don't know if they are linear. So I go there with a quadratic one. So what I expect is that the problem, the estimator itself is telling me, say, okay, don't put c, because c is clearly wrong. Okay? Now what we do is we organize the data to be symmetric. So which means our samples are between plus and minus. Okay? So for this reason I take H2 transpose H2 as C page something. I go to C. Okay? So that is equal C page page 4 if you like. Page 4 up to page 6. So this is equal to, and let me make it very simple. So a term that is different from 0, 0. A term that is different from 0. Then 0. Term different from 0, 0. Then term different from 0 and different from 0. Every time I write this star means the term is different from 0. Okay? The numerical value is the one that is in the previous, is 2 pages before. Then here, what is H2 transpose H1? Okay, so T0 transpose, T1 transpose, T2 transpose, multiplied by H1. And H1 is T0, T1, multiplied by A1, B1, plus the noise. And my goal is to see if it is biased. So there's this. This one is T0 times T0. T0 times T0 is N. So that is N. Then I have second term. T0 times T1. 0, right? T1 times T0, 0. T1 times T1, okay, it's different from 0. Put it this way. Actually, that would be n cubic divided by 3. Never mind. N cubic divided by 12. Never mind. Then I have T2 multiplied by T2 transpose T0, different from 0. T2 transpose T1, 0. Okay, everything multiplied by A1, B1, plus and minus. So, star, 0, star, 0, star, 0, star, 0, star. Every time, star means different from 0. Now, what's happened? What is the term I'm interested in? The term I'm interested in is C2. Because I expect C2 to be 0. So, what is a C2? So, if I need to look at C2, I need to make this, okay, that one multiplied by that. So, because that is the term. Now, this one.
The first matrix is not to the minus 1.
No, I already computed the inverse. I assume I made the inverse. I put a star for this reason because I didn't do the inverse. Okay. So what I found is that in our multiplication, this term is different from 0. Multiplied by n this term, different from 0, multiplied by another term that is different from 0. So the bad news is that it comes out that the last C2 is not equal 0. It is different from 0. And you know, it depends on A1 and A2. So if rather than writing this way, I can write that I have n A1 plus B1 is 0, then it is B1 dependence, then it is A1 dependence. So you know, I have a different mixture of terms. So the last term depends on B1. So you know, here I have a dependency on A1 and B1. So that means that C2 depends on A1, B1. But you know, the bad news is that C2 is not 0. So C2 is biased. That's the conclusion. Conclusion is, if you try to estimate with, if your model is linear, or if your model is a certain model, and you are over-parameterizing, which means you're using more parameters than necessary, what you expect is, you might expect, as in this case, you might expect that the estimated value is different from 0. It might be random, but it's different from 0, which means it's biased. Because you know, the true value of C2 is 0. Because we are working with a linear set of parameters. But you know, no matter that the set of parameters is linear, I get a C2 that is different from 0. So even if you know my parameters are linear, I get some curvature. I get a certain C2. Second, you know, this C2 which comes from that is noisy, because it depends on the noise effect. So at the end of the story, the bad news is that if you overestimate, so if you estimate more parameters than necessary, what you get is that the estimated parameter might be biased, because might be affected by the previous parameters, and you know, they're noisy themselves. And the noise, you know, might increase too much, so this noise term might be intolerable. So there is a trade-off usually. So you can do the same discussion in the opposite way to see, is it always appropriate to over parameterize a model, or is it wise, or is it better to under parameterize? Now, I conclude this simple example by saying that in practice it's always better to under parameterize the estimation of a set of parameters rather than over parameterizing, which means estimating more parameters than necessary. Because if you estimate more parameters than necessary, if you are unlucky, as in this case, and your estimated parameters are not 0 in the mean, and which means it's biased, and they are affected by noise. So you can really not understand if in your system that parameters matter or not. Now, this is the sense of this exercise. Now I told you I want to make at least a start of this exercise. Now derive, this is taken from some exam. I don't remember, I didn't put the exam here. So derive with a clear definition of the assumption of the maximal accurate estimation for continuous signal inactivity white noise model. Perfect. Okay, easy. See the book. Which means, you know, I write the book, you need to write it. Huh? Okay. Now I go to the second one. Consider estimating the frequency of the sinusoid and its amplitude in white Gaussian noise W from the observation interval T, and the signal is a sinusoid. Here. Define and derive the maximum molecular method. Fine, but I want to go to the most complicated part, which is it's increasing. The complexity is always increasing, okay, in the exercises. So, derive, blah, blah, this is book. Now, evaluate the covariance and the camera bound and comment the results. This is what I want to go. Now, if I want to calculate the camera bound in this case, I need to create the Fisher information matrix. So I need to go to see how to make the Fisher information matrix. Now, how many parameters are here? There are amplitude, frequency, and phase. So the three parameters, my theta parameter are amplitude, frequency, and phase. Look at the problem is different from the previous one because this is continuous time. The other is discrete time. Okay. So I need to write the Fisher information matrix. Okay? So I can write the Fisher information matrix on amplitude. I'm writing the Fisher, which contains amplitude, omega, amplitude, phase, omega, amplitude, omega, phase, and then I have Fisher on phase, amplitude, which is the same as before, and then Fisher on phase, omega, and then Fisher on phase. Okay, now let's calculate together. Now, amplitude. So the Fisher information matrix is by taking the model and calculating the derivative of the model with respect to the amplitude. So in order to calculate, since we are running out of time, so I need the distance. So I need to calculate the derivative of A cosine omega 0 t plus p with respect to amplitude. I need to calculate the derivative of A cosine omega 0 t plus p with respect to omega 0. I need to calculate the derivative of A cosine omega 0 t plus p with respect to phase. So let's start with first. This is the easy one. So the partial derivative with respect to the amplitude is cosine. Okay. Now, what is the derivative with respect to omega? Well, I have A. The derivative of cosine is minus sine. So it's minus sine of the argument, and then it's the derivative of omega 0. It's a t. Okay. So it's minus A sine omega 0 t plus phi, and then multiply by t. Group t here. Okay. Then, what is the derivative with respect to the phase? Well, it's easy. It doesn't need, it does not contain the derivative with respect to the omega 0 t. So it's a minus A sine omega 0 t plus phi. Then, if I need to calculate the CRB, give me 2 minutes. It's almost done. So, if I need to calculate IAA is simply 2 divided by n0, and then it's the integral of cosine of omega 0 t plus p square dt. Computed from 0 to capital T. This is by the formula of the Fisher information method. This is the power of the sinusoid. So, this divided by t makes 1/2, right? Okay. Integral of cosine squared dt divided by t 0t is equal to 1/2. Okay. Then I keep on repeating this this property. So the property here is it is 2 times and 0. Then it's 1/2, so it is t divided by 2. Okay. So what is a? Let's compute a and omega 0. Then it's 2 times and 0 integral 0 capital T. Then I have minus a. Then I have cosine omega 0 t plus phi times sine omega 0 t plus phi multiplied by t dt. Okay, now, so what is this? This is sine of 2 times omega 0 t plus 2 phi. Okay. Then I have integral of t multiplied by sine of 2 omega. This is equal to 0. Surprising?
Over 2.
Hmm?
Sine of 2 over 2.
Yeah, over, yeah. But since it's a 0.
Yeah.
Okay. Now this one is equal to 0 because, I have a t function and a sinusoid. Let me sketch it. This one is, the star, okay, is, I have a growing, this is t multiplying t, and then I have a sinusoid that is going up and down. Every positive has a negative. And when I sum the terms, the sum is 0. Because I have positive, negative, positive, negative. Okay? Now, you need to see that the sinusoid is very, very high frequency, so the period is very small. And so the change is very, very, very rapid. And so when I calculate the integral, I calculate the area. So it's the area of the product. So for this reason, okay, the integral, let me say, the integral of that one, okay, is a nice writing. It's a very fine writing. So the integral for that one, in dt, is equal to, actually it's approximately, okay? It's more 0, so it's very much 0, if the period capital T is very large. So there are some constraints on that. If the capital T is large enough, we say in engineering, okay? If the frequency is small enough, because for instance, if I take the period that long, and the sinusoid is very slow, this approximation does not hold, okay? So this approximation makes sense if the period of the sinusoid, so what is the period? It's 2 pi divided by omega 0. The period of the sinusoid should be much smaller than t. Okay? So this is the constraint. This is the period of the sinusoid.
The period, we talk about the sine of 2 omega 0, so the period is half, right?
Oh yes, it's 2 omega
2 omega 0.
So in the integral formula, you said that the integral of cos squared is 1/2. Then you're just integrating over one period, right?
I'm integrating t.
Yeah,
T is very big.
Yeah, big T is very big.
Yeah.
Yeah.
So it's many periods.
So it's many periods, but if you integrate cos squared over many periods, then it's more than 1/2, right? Because cos squared is possible.
Are you talking about this one?
Yes.
Okay. This one is, this is if these all's on one period.
Yeah.
Okay, but if you take a 2 period, so if t is multiple of the period, then it's exactly 1 hour. Now, the question would be if capital T, which is the integral, is not exactly an integer number of the period of a sinusoid. Okay. Now, since this is not always guaranteed, then this is approximately 1 hour.
Yeah.
Is that what you mean?
Yeah.
Okay. I continue on that tomorrow. Okay. I put on Dropbox. I'm cleaning a little bit. Put on Dropbox so that you can prepare tomorrow. But I continue on that. And then I randomly choose other exercises. Okay, for tomorrow.